Okay, so this is the lesson on BJTs. Yeah. So yes. Okay. Anyway, so what is a BJT? I'll give you an example of what a BJT does. Okay. Imagine like if Ninja got a low taper fade. If there's uh, a river, and then like there's like a board or something, or like a dam or whatever blocking the river's path. So that means, okay, now the river is being blocked, right? So if you have water coming down, it doesn't go through. All right, ignore the fact that, yeah, it doesn't go through. All right, then imagine we have like another stream of water coming in here as well, and then we say, if the stream of water is strong enough, it can actually push this boundary, right? And their streams combine together. So now this is a strong stream. Yeah. Or we also say if the stream is strong but not that strong, it can lift it a little bit away. So not all of the big mainstream and not all of this little stream goes through, but it does go through. Okay, so that's the analogy. And this is basically a BJT. Alright, so I shall draw for you the two symbols of a BJT. Okay, basically there are two types of BJTs. NPN, which is the one that which the analogy that I just showed you fits the NPN, and the PNP. Okay, let me label these. Okay, let me bring these a bit lower actually. Yep, and they look like this symbol form. Like so, okay. And actually, you need to know the how the um how the configuration of these BGTs look like. So for NPN, right, it looks like this. Okay, if you don't know what I'm talking about right now, go and watch the video on diodes, and then it'll make sense. Okay, so NPN and then PNP, like so, and then kind of looks like this. So you can see how it's corresponding to the on above, yeah, like that. So and this, yeah. So that's the configuration for NPN and PNP. I'm gonna make these smaller if I can. Yeah, I can. Put them on the side. Okay, I won't be talking about PNP a lot in this video. Maybe in an upcoming video I'll talk about it more. But yeah, okay. So I'll be doing most of the lesson on the NPN now. Alright, so with the NPN transistor, or with transistors in general, right, there are some properties of the transistor that we can label out and actually do some calculations with them. So there are three currents that you need to know for the transistor. Right, they go in this way, and that is C, IE, and IB. And I forgot to mention, right, these legs of the transistors have names. This is the collector leg, this is the emitter leg, and this is the base leg. Right. So that's for current, and then there's two voltages you need to know. The voltage from C to E is called VCE, and the voltage across B and E, B as like base and E as an emitter, is VBE. And one thing to note about this connection here is that this connection acts like a diode. So it allows current to go through one way but not the other. Alright, so yep, that's pretty much all you need to know about the BJT. Next are two equations that you need to know. First is that IE, which is the emitter current, is equals to the collector current added to the base current. So that's neat. And with the next equation, right, with every transistor comes something called gain, or the transistor's gain. And you can find the gain of a transistor, which is denoted with beta sign and then DC, is equals to IC over IB, I think. Yeah, IC over IB. Nice. And that's pretty much all the properties you need to know about a transistor. Okay, now let's talk about regions. Regions. So there are three regions of a transistor you need to know. The cutoff region. Oh my gosh. The active region. And the saturation region, which I'm just going to say sat region. So, okay, and I'll talk about all of these. So the cutoff region is when IB is 0, and in a practical BJT, IC is like very,
Chatbot said
very,
teachers slave
very,
undeafen
very close to
themselves.
0. Oh, and Jovia is back. Yeah, Jovia has been gone for, I think maybe not that long, but he's been gone, yeah. And he's back now. So that's the cutoff region. The active region is when IB is higher than 0. Then IC is higher than 0 lah, yeah. So that means if like IB is higher than, yeah, higher than 0, then IC is higher than 0. Yes, pretty normal. Alright, yeah. Then saturation region is right. Okay, if you keep increasing the current of IB, IC increases as well, but there'll be a certain point, right, where you reach the maximum current that like the battery or the power source can provide. So then the BJT will be in saturation region, where no matter the current of IB, IC would remain at saturation, and is denoted by IC sat. And at saturation region, VCE is known as VCE sat. Yeah, something like that, pretty much. So that is all to transistors, I think. Yeah, pretty much. So let's move on to something called the Darlington pair. Okay, so what is the Darlington pair? It's a configuration of two or more NPN transistors actually, and the configuration looks something like this. So I'll draw a simple circuit. Oh wait, did I draw the? Yeah, I did. Alright, I drew it accurately. So so hard to draw. Wait, what? Wait, what? Yeah, okay, that's okay. I can make this look better actually. Hold on. Jovia, I'm right? This is how it looks. Alright, there. Okay. So what is the point of a Darlington pair? Thank you. Okay, so what's the point of a Darlington pair? Basically, right, it's used to amplify current. That's basically it. And you know how I was talking about current gain? Well, DC current gain. Oh yeah, the gain. Yeah, I forgot to tell you. I said that it's called transistor gain. The gain of transistor. It's formerly known as DC current gain. Okay. So whenever you use a transistor, right, as a switch or whatever, um, the current, right, the output current, i.e., as I have said, will be increased. It will be IC plus IB, and in here, right, we can find the output current, which is okay, the current gain. Sorry, we can find the current gain of both of these by multiplying the current gain of the first transistor with the current gain of the second transistor. So I'll just say this, yes. So yeah, that's Darlington pair. And okay, stupidly, I forgot to mention what a transistor is mainly used for, which is damn, right? Crazy. So a transistor is used as a switch. So let me give you a simple scenario. That's it's an LED, BJT, ground that stuff. Yeah, and then power, whatever. Yeah. So this is an example of using a BJT as a switch. So when this switch closes, right? Okay, no, when it's open, okay. IB, I mean I, yeah, IB is 0, and when IB is 0, um, the transistor will be in the cut-off region. So IC will be 0. So this would act as an open circuit, so the diode won't, I mean the LED won't turn on. But when I close this switch, then okay, these are the same, right? These are exactly the same. So when I close the switch, the transistor will actually go into saturation region because the current at IB will be high enough for IC to reach its saturation, and then the diode turns on. That's a terrible explanation, but gets the point across that the transistor is basically used as a switch. Alright, yeah, and the main upsides of a transistor as compared to just using a switch is transistors are more can be automatic switch. Yeah, we're not getting into that. Okay, why transistor better? Okay, numero uno. Transistors. I know these. Um, Bro, I was saying three. There are three main upsides to using a transistor. And I was saying them to myself like a few seconds ago, but I forgot all of them somehow. Okay. Switching reliability. Oh, okay. Number one, it switches faster. Okay, it switches faster. Number two, it does not deteriorate faster. It does not deteriorate it as fast as mechanical switches. Okay, because mechanical switches have like metal and stuff, and then when you press it, it bounces off the contacts, slowly deteriorating the contacts away. Well, guess what? A BJT does not have all that contact nonsense. It lasts way longer. Um, and then the third one, I don't know. Uh, okay, well, I don't really have to teach it to you. I'll find out later. Alright. Okay, but basically, this is all you need to know to pass. Okay, BJT question. So yeah, will be sent. Yeah. So let's look at a BJT question. Okay. Um. Yes, I've been recording. Yeah. Okay. Yeah. So this is a BJT question. Um. Sorry, a bit rearranging. Okay. Let's go ahead to answering it. In the circuit shown in this figure, an NPN BJT is used as a switch for a bulb rated at 5 volts. The bulb has a resistance of 250 ohms. The bulb should reach near full brightness when V in, which is here, reaches 3 volts. Determine suitable values for VCC, which is here, and RB. RB is, okay, this resistor. And then they give us some information about DC current gain, VCE, saturation, and VBE. Alright, cool. So I'm gonna answer the easiest question here. What VCC should be? They tell us that the bulb is rated for 5 volts. So honestly, we can just say okay, that's thick. VCC is 5 volts. Okay, it's not that deep. It's that simple. Okay, so 5 volts. Now we need to find RB, which is a little bit more complicated. So let's take it one step at a time, and then let's annotate on the diagram given to us the information that is given to us. So V in, they want the bulb to be at full brightness when V in is 3 volts. So V in is 3 volts. Ding! Alright. Um, DC current gain is 40. VCE set, which is this. Okay. VCE set is 0.2 volts. And VBE, which is this, that acts like a diode, is 0.7 volts. Alright. Beautiful. Some spit on my screen. Okay, anyway. So that's all the information that is given to us. So and then we define RB. So how can we find RB? RB, okay, we know R is equals to V over I. And if we just take a look at this part of the circuit here, so we have a resistor, and then we have a diode. Okay, as I said already, it's a diode. So 3 volts, RB, this diode, that is 0.7 volts, and then we have the current here, which is IB. Okay, and we want to find RB. Okay, so R is equals to V over I, and actually right now I can add more information. Oh, okay, I wrote in such a way that I have to shift things a bit too. And right now we can actually add more aspects to this equation to help us more. For V, right, in previous videos, we can actually find the voltage across RB. It will be 3 volts minus 0.7 volts, obviously. And then I is actually IB. So look, we're one step closer to finding RB already. Now we just need IB. Okay? So, shit. Okay, yeah. So how do you find IB? Well, actually, we know that DC current gain, which is 40, is actually equals to IC over IB as well. So if only we could just find IC, then the question is solved. And we can, okay? IC is here, and if we just take this, this part of the circuit, which looks like this, the bulb, and then ground, and then this part is VCE, which is 0.2 volts lah, and then this is 250 ohms, 5 volts, and then this is whatchamacallit, IC, IB. Okay, in a series circuit, the current is equal, but in this case, it's not, okay, because there is some other things at play, but this is just a model. So, yeah, right. IE, not IB. That's an E though. Sorry, yeah, alright. Yeah, okay, so we need to find IC to eventually get IB. So, can we do that? Yeah, we can. Because using IC is equals to V over R, we can actually just take 5 volts over 250 ohms, right? Right, Jovaya? And if we calculate this, we get 0.02. Jovaya, am I right? Or do we have to minus 0.2 volts first? Uh, hmm. Well, luckily for me, I've already solved this question before, like 5,000 years ago, so I can just check. What a lesson. What? Why is there no picture of it? Okay, it's a previous video. Yeah, this, okay. Today's explanation of how to do this video is, how to do this question is so ass. So I would suggest for you to just go to this video that I'm going to figure out how to do this question. So, okay. It's the exact same question, by the way, guys. Right and uh-huh. So now we just need IB and then uh-huh. So now knowing that, right, we want the voltage here. Since this is 5 volts and that is 0.2 volts, then the remaining voltage will be here, and that will be 5 volts minus 0.2 volts. Okay. Yeah, okay. So the reason for my confusion, right, is because of a misunderstanding of the law that IC is equals to IE right now. Okay, in a series circuit, which I've already mentioned, the current, right, is equal in a series circuit. But in this case, it is not. It's not. Okay? Because of some other elements at play. So IC is not equals to IE. And in this case, we have to take 5 volts minus 0.2 volts to find the current IC, which is independent from IE. So in this case, we do this. Okay. So we have IC, And okay, let me just get a approximate calculation here. 5 minus 0.2 divided by 250. Okay, so it's 0.0192, and we can plug it into this. So 40 will be equals to that over IB. So IB would be 0.0192 divided by 40, which is equals to 0.00048 crap amps. Yeah, sorry, amps. Yeah, okay. And then with this, we can plug it into this. And then our final answer would be 4791 ohms. And then it's just 4.8 kilo ohms. Yeah, okay, so if you were trying this question and then you got 4.8 kilo ohms, you're right. Yep, because that's the answer. Yes. Okay, so we you just learned BJTs. So yeah. Um I don't know what else to say. This was a pretty shitty lesson, one of my worsts. But with this information, which is also the information that I have, you will be able to do your BJT questions. So thanks for watching.